Thank you very much, and welcome to my presentation. Today I'd like to present the results of the research, which is a section of a broader research and experiments done for INSNAC project. And we're going to be presenting results of the research on the impact of our intelligent science system on the maintenance of the minimum distance by the drivers. The presentation plan is pretty standard. First, I'll introduce the basic facts, then I'll discuss the method, the experiment, and then we'll have a conclusion. In terms of the motivation for the research itself, I'll allow myself to explain in greater detail what INSNAC project is. During that project, our task is to prepare such type of intelligent road marking that will interpret the parameters of the traffic in the location of its installation, and then via displaying different types of messages inside or in a different location, it will attempt to achieve a certain desired effect. And the algorithm that does that in those tests that we carried out is what we did. We prepared that algorithm. So we were inspired by Egypt's approach, so kinematic. We assumed that we wanted to maximize increase the minimum distance between vehicles on the road at a given section of the road, and wanted to do this based on the recommended speed and based on the data that we collect from the road. The data we collect through an array of sensors. There's quite a lot of them. There's Doppler, there's LIDAR, there are weather sensors. There are actually some more advanced detectors, such as a vector acoustic detector that, in addition to recording noise, can also record the direction of the noise. So this research is, in our case, based mainly on simulations, because we suggest a certain way of selecting the recommended distance based on sensor data. So the starting point is the measurements that we done at Lipowa Alley, not far from Gdańsk, in the village of Leźno. This is a road where there's a speed limit of 90 kilometers per hour, and in the simulation, where we have a Kurowski-based model implemented in the Sumo simulator, that's where we run the tests of our algorithm, which is supposed to maximize the minimum distance. That data was collected over a long period of time in 2019, from May to September. Therefore, we were able to eliminate quite a number of non-typical or unwanted preferences, for instance, the impact of weather. So we were able to compensate for the impact of weather. This is a visualization of the road section on which we operated, which was digitally transferred into the modeling environment. So once we simulated this road in the digital domain, we were able, therefore, to run it with different iterations of the algorithm and with a variety of simulated parameters. What is important is it's important to emphasize some of the assumptions for the system. We assume that the effect will be the impact will take place at the entrance, based on the entrance. So this is quite a localized influence. The measurements are taken on entrance of the section. The data is processed automatically. We can do it automatically because we run quite a number of simulations. There were many different sets of parameters that we tested, and that is why we used Python scripts which automated the Sumo simulation. We used Trassi interface, among other, which is made available in the Sumo simulator. So to simplify, we assumed that the drivers would always follow the recommended speed. It is also important that we assume that we can only lower the speed. in a given application place. So if there is a global limit of 90 kilometers per hour on that section, so even if some calculation might suggest that we could go 91, we assume that we're not recommending that. We're not allowed to. So as I said earlier, we were inspired by NIP's model, where we analyzed distances between vehicles, and that is why the structure of the reasoning is kinematic in nature. We assume that the average distance between vehicles at worst should be sufficient to, first, for the driver to be able to react to threat, and secondly, to be able to completely stop the vehicle. And that is presented in the equation at the bottom of the slide. We have the braking time, dBr, and that braking time is divided into reaction time and mechanical breakage. And that equals so the braking time plus reaction time equals the minimum distance. Putting that formula in some sort of order, we have a square formula, and we then put velocity as a variable. And there's also the limitation, which is the upper limit of the velocity, 90. We know that if we maintain the maximum, so the recommended speed is one that will allow the driver to react and stop in case of a dangerous situation. So what we need to know is how quickly the vehicle can decelerate depending on the road condition. We can measure that from cameras. Reaction time is one of the things that we just have to assume. Depending how conservative we are with safety, we will assume the relevant reaction time. Simplifying this, that's what the solution of that equation looks like. V recommended, and the deceleration in dry is 7.5 meters per second. That's for dry road surface. So this is how it was assumed for the system. The one problem that we faced was to estimate, based on this data stream, of the median distance. So we simulated this mechanism, because the simulation was supposed to give us a certain idea of how to do it in practice. So we're using here an approach where we measure the average speed of the vehicles. We divide it by the number of vehicles that cross the monitoring per unit of time, and then we adjust it for the average length of the vehicles. And these are the values that we can use. You can, for instance, use a LiDAR to count the vehicles to put in the numerical, or we can use the camera's signal, where we can evaluate the traffic structure. Based on that, we can then evaluate or estimate the mean length of a vehicle. And based on that, we can evaluate or calculate the recommended minimum distance between vehicles. Now, how did we actually do this? For an individual set of parameters, because we did fiddle a little bit with reaction time. We had three different parameters from 850 to 1,500 milliseconds. And also we varied the number of vehicles per hour, 400, 800, and 1,200. So for each of these, we run 40 repetitions of the simulation. Each simulation consisted of two parts. First, the situation was simulated when the system was not on, and then it would be turned on and apply a speed limit. And then there was a simulation in which the system was on. So based on that, by subtracting one distance between vehicles from the other, we would see the signal of correction. If it was positive, then we knew that on average that distance between the vehicles was increased. And that is what we want. And this is the visualization of the results. This is a box graph that came out of this data and simulation. We can clearly see that there is a key impact on traffic intensity, so the number of vehicles per unit of time on the section, but also reaction time. So based on this, you can notice that our solution gives more repeatable effect if there are more vehicles. For 1,200 vehicles, the results were much more visible, much more apparent. For 400 vehicles per hour, usually you could see that you see the lower extension of the lowest estimated observation was actually negative in value. It is also worth noting that for all observation groups that have been visualized in the graph, we can see that the lower quartile of the improvement is positive or at worst close to zero. So we had a positive effect for at least 75% of the vehicles, where we were able to actually increase the minimal distance between vehicles, the minimal average distance between vehicles. We also have the reference sequence of zeros. That's the end. And this is needed for the analysis of statistical significance. It will be much more comfortable if you look at it in the paper, actually. But the general conclusion is that when we have values typical for more traffic intensity, and if we have higher time constants, then the statistical impact is higher. What is also important is that if we compare it to the reference values, which is a sequence of zeros, we proved that everywhere the improvement has a median higher than zero. So the system worked every time. But it was not always sensitive to the change of parameters. So the sensitivity to changing parameters is higher if we have more vehicles on the road. It's also worth noting that the between quartile zone decreases with increased traffic, so that makes the results more repeatable. That's worth remembering. And moving on to the conclusions. In the simulations, we've managed to observe some phenomena which are desirable from our point of view, in the sense that we affected the distribution of the distances in moving it in the desired direction. But we have to remember certain limitations, or especially the features of this research. It is a simulation, after all. So any errors, any numerical errors that could happen in them would need to be at all times verified by on-site measurement, even though we did have a certain traffic-based calibration from a long observation period of traffic. We also have to remember that there is a certain local characteristic for the application of this system. We have data from only one road section. It could differ depending on where we want to install such a system, and that variability is perhaps the introduction for further research. We need to determine the variability. Maybe in certain conditions those distributions would be inferior in terms of system application. I think that is probably a complete summary of the main thoughts. But I also like to emphasize that the project is financed by the Polish National Center for Research and Development. Thank you very much for your attention.